Earlier in my career, I was director of engineering at Google for Google App Engine. So that's Google's platform as a service, like Heroku, which you might be familiar with. And then earlier on, for about 6.5 years, I was chief engineer at eBay. And I helped eBay transition through multiple generations of their infrastructure, in particular the real-time search engine. So a little bit about Stitch Fix, because I doubt that very many people here will have heard of it. That's because we're mostly in the United States. Well, all the United States. So the idea here is, rather than going to a store or going online and choosing the clothes that you want, let's see if we could get an expert to help you. So the idea is, you come to Stitch Fix, you create your own style profile. So you fill out a list of 60 to 70 pretty detailed questions about things you like, things you don't like, things you wear, styles you like, price preferences, all that kind of stuff. We send you 5 hand-picked items in a box. Those items are hand-picked for you by an actual human. You keep what you want and you return what you want. So how does this actually work? Behind the scenes, there's a ton of art that, as reflected by the humans, and a ton of science and data science as reflected by the machines. So one thing that's pretty unique about Stitch Fix is our commitment to data and to data science. So we actually have a 1-to-1 ratio between data science and engineering. So we have roughly 70 software engineers in the team that I work on, and we also have about 70 data scientists and algorithm developers. I would love to be proved wrong here, actually, or to hear the counterexample, but as far as I'm aware, this is actually unique in the industry worldwide. So I'm not sure I've heard of a company at our scale that has equal numbers of, equal amount of investment in engineering and in data science. And because of those 70 data scientists, you might ask, what in the world do they all do? I mean, they all have PhDs and stuff, so what in the world are they doing? It turns out that being smart pays. So we apply intelligence to every part of our business. I'm going to talk in detail about one in a few slides, but we apply it to every part of our retail business. And we're actually a physical business, so we handle physical goods, we ship them through the mail, and we store them in physical warehouses. So we apply data science to buying of the clothes. What should we buy? What styles are going to be on trend in 6 months from now? How much should we buy now? How much should we buy later? What warehouse should they go to, et cetera. We apply it to inventory management. Where should we store things? Where should we ship them from, et cetera. We apply it to logistics optimization. So when somebody is picking those 5 hand-picked items in a box, that can't be today done by a robot. So what's the path that we should send that picker through the warehouse to find those 5 items? For computer scientists, that's actually a traveling salesman problem, so NP complete. Styling recommendations, which I'm going to talk about in more detail. How those human stylists decide which 5 items to put in the box for you comes with a ton of data science and algorithms behind it. And also more standard things like demand prediction, right? Again, because we have a physical business, it's really important for us to know ahead of time how many customers we're going to have, how many boxes we're going to send, et cetera. Because if we get that wrong, either by overshooting or undershooting, we're going to have either too many stylists, too many warehouses, too much inventory, et cetera. The general focus here is combining the best about humans with the best about machines. So I'll give a particular example of styling. So when we say styling, what we mean is choosing those 5 items that are going to go in the box that we send. So we have a bunch of physical inventory, and from the customer perspective, all they know is that they have a personal stylist, just like a rich person, and then they receive stuff in the box that hopefully they enjoy. What's behind that is a ton of data science and algorithms. So the first step is looking at that inventory and looking at the client preferences, doing a ton of machine learning with a bunch of different models and a whole ensemble approach that comes up with a set of personalized algorithmic recommendations for that particular client. So when I say algorithmic recommendations, a way to think about that is it's like a search engine that puts things in ranked order, except you get to see the scores, right? When I say you, I mean the stylist. So those scores are our prediction about whether this client is going to keep this item if we send it to them. So Randy has a 47% chance of keeping this shirt, a 36% chance of keeping these shoes, a 57% chance of keeping these pants. Actually, those would have been bad predictions because all these things came from Stitch Fix and I did keep them. So there you go. So given those algorithmic recommendations, then we could go through the human curation step. So that's the styling part. And we have 3,500 human stylists all around the United States that are employees of the company that are choosing, based on those personalized algorithmic recommendations, what are going to go in those boxes. And what has worked for us is the combination of having the machines do what the machines do best, sorting through tons of data and making those quantitative recommendations, and the humans doing what the humans do best, like what's on trend, what constitutes an outfit, what would an engineer in Silicon Valley actually wear to work, that sort of thing. The things that humans know that machines don't. So now I do actually want to talk about microservices, but we're going to take a few steps along the way. So I want to talk about how we work and why how we work works for us. So modern software development is not just about technology. I hope we all recognize that. It's actually a combination of organization, of processes and practices, of culture, and of technology. And I'm going to spend a few minutes talking about the organization, the practices, and the culture part, and then I'm going to spend the majority of my time talking about the technology part. So in particular, if you took one thing away from this presentation, it would be this: organization, small teams; processes and practices, test-driven development and continuous delivery; culture, DevOps; technology, microservices. So nothing else. These are my recommendations. Go do it. Okay, let's talk a little bit about small teams. So at Stitch Fix, just as I experienced at Google, just as you would see at Amazon or Netflix or a bunch of large high-performing companies, we do a similar model, where we have our software development teams directly aligned with business domains. Those development teams have clear, well-defined areas of responsibility, and they typically maintain a single application or a single service or set of related services and applications. Those teams are cross-functional, so the team has inside it all the skill sets that they need to do their job. And that doesn't mean all skill sets in the world. Like, we're not making our own hardware, and we don't have, embedded systems engineers. So we do depend on other teams and other third-party services to do other stuff. But for the primary job of meeting that business function, the teams have within their boundaries all the skill sets that they need to do their job. Practices. So we practice test-driven development, and we practice continuous delivery. So test-driven development, why would we do this? It's not because we want to be slower, it's actually because we want to be faster. And tests help us go faster. Tests have my back, right? So if I make changes, I know that the tests are going to tell me if I've broken something. And it actually ends up increasing our velocity, increasing our ability to deliver features for the business rather than slowing us down. It's absolutely an investment that we make up front, and we completely recognize that, but that investment pays off every single day that we run those tests in an automated way. Tests make better code because it gives us the confidence to break things. It gives us the confidence to refactor what otherwise would be ugly, crufty code. Has anybody had an experience in their own lives where they're afraid to touch something because they don't know what would break if they do it? Yeah, most of the people. Me too, by the way, which is why I love this way of working. Tests make better systems. By having automated tests farther to the left in our software development process, meaning earlier in our software development process, we're able to catch bugs earlier, and we're able to fail faster with a tighter feedback loop. Continuous delivery. We also practice this. What does that mean? It means that most of the applications, and we maintain about 40 different applications and maybe another 40 or so software services. Almost all of those applications and services are deployed multiple times a day. They certainly all can be if we want to. This leads to more solid systems. It allows us to be able to release smaller units of work. If you subscribe to the lean methodologies, this is smaller batch size. It means that those small units of work are faster to repair in case they go wrong. They're easier to diagnose. So if there's an issue, we can figure out what it is because we've only changed a small amount of code. And of course, those small changes are really easy to roll back and to roll forward in case there's an issue. It enables us to do experimentation. So since we're in such a data-driven world, A/B testing is super important to us. And so this gives us the ability to make small experiments and do rapid iteration because this stuff is really cheap. Now I want to talk briefly about DevOps. So what I mean when I say DevOps, and lots of people mean lots of different things, is that teams have end-to-end ownership of all the things that they build and run. So the team owns their service from the design phase through the deployment phase, all the way through to retirement. When I started in this industry, and you can look at me and tell that was a while ago, when I started in this industry, software engineering was done when we finished committing our code, and then there were some other mythical operations people, or actually in the places that I worked, other people at other companies that we shipped software to on CDs. Does anybody remember that? We shipped software to those people, and those were the ones that actually operated the software. Well, now that's not how we work. Now, the same team that builds the software also makes sure that it has good quality, that it has good performance, and that it operates well. So developers on those small teams are responsible for all aspects of the development lifecycle: the features, the quality, the performance, the operations, and the maintenance. We don't have separate teams or even separate humans that do QA, that do operations. It's all the same group of developers enabled by a bunch of tooling that we have to do all those things together. And it's basically a reification of the Amazon idea of you build it, you run it. Okay, that was a quick tour through the background of 3/4 of modern software development, and I'm going to spend the rest of the time talking about about microservices. So microservices, lots of people have lots of definitions. To me, it's about, the micro means the size of the interface. So a microservice is single purpose. It has a simple, well-defined interface, and they're modular and independent, which means that I can combine and compose and recombine and recompose microservices to do new and interesting applications. Microservices, though, the word is new, but the concept is really old. To my mind, microservices are nothing more than service-oriented architecture done properly. The one thing that you need to add, though, and the one thing that most service-oriented architecture re-architectures got wrong, which is why it got a bad name, is that microservices have a low surface area in their interface, but also own their own persistence. In other words, each of those individual microservices has its own database or its own persistent storage mechanism that it doesn't allow people to directly access. So I'll talk a little bit about some techniques for how to make that actually happen. So the first obvious approach is that the same team that builds the service owns and operates a database, right? So we use Postgres at Stitch Fix. So we might store, an application or a service might store to its own instance of Postgres. It might have its own instance of a search engine. But those things would be owned and operated by a service team. And this is a completely legitimate approach, and we actually take advantage of this directly ourselves. The other approach, which we also use, and which is also available to you, is use a service that somebody else provides for persistence on your behalf. So store to your own tables or your own spaces in some third-party service, whether that third party might be another team within your own company or maybe a cloud provider, right? So if you're talking about Amazon Web Services, you might use a service called like Dynamo or like the RDS, the Relational Database Service. If you were using Google, you might use one of their services like Bigtable or like Spanner. But the general idea, though, is that you have your own little isolated slice in a multi-tenant environment that somebody else is operating on your behalf. And either of these mechanisms are pretty straightforward ways of getting what we want, which is that nobody gets to touch my data except through my published interface. And that's the critical idea here, is that for a microservice to be truly effective, the only way that anybody should be able to get external access to data, in or out, is through the published service interface. Does this make sense? Cool, lots of nods, excellent. Okay, not every company started this way. In particular, Stitch Fix, I will say openly, we avoided the temptation to build a monolithic application, but we absolutely built a monolithic database. And this is something that we're dealing with right now. So the problem is that I mentioned we have 40 different applications. Well, the vast majority of them are actually are calling into a shared database that has essentially all the interesting entities for our business, right? So at the moment, the shared database has all of our clients, all of our shipments, all of the items that we have in inventory, all the styles or the SKUs of the things that we sell, all the information about our warehouses, et cetera, et cetera, et cetera. So this is a major bottleneck both for development and for sort of performance and for and a single point of failure. So we want to get away from this. So what are we going to do? The goal here is that we want to decouple our applications and services from the shared database. So let's talk about some steps about how we're going about doing that. But let's make a slightly simpler example just because otherwise there are way too many lines and boxes on the diagram. So let's imagine we only had 2 applications instead of 40, and let's imagine we only have 3 tables instead of whatever, 170. So 2 different applications each talking to 3 different tables in the database. So the first step that we want to do is we want to create a service around one of those tables. So in this particular example, I'm creating a service around clients. Now, that service is still talking to that table in the shared database. So once that service's interface is good enough, we migrate the apps to, instead of talking directly to the table, they talk through the service to the table. So now the applications are decoupled from the service, but the service is still persisting its data in the shared database. So the next thing that we do is that we simply extract the table from the shared database. You know, there's actual work that's done here. But we extract the table from the shared database into a database that is local or private to that particular service, and now we're good, right? So now we can draw a line around the client service and the data that the client service stores. That's our microservice. So the next step is we just keep doing this over and over again, right? So we rinse and repeat, as we like to say on shampoo bottles. So we do the same thing for the items, for the core item table and for the item service, and we do the same thing for the core SKU or the core style table and the style service. Does this kind of make sense, at least conceptually? Yeah, lots of nods. Excellent. Okay, cool. And by the way, if this makes it seem like this is trivially easy, it totally isn't, right? Unhooking those tables from other applications and other services that are interacting with them, that's the real work. But this is the general conceptual approach. Take it one table or one set of related tables at a time, one service at a time, and just keep moving forward and forward and forward, right? There's the funny joke, how do you eat an elephant? One bite at a time. So how do you undo a monolith? One service at a time. Okay. So the next thing I want to talk about in sort of, effective services in a data-centric world is I want to talk about events. So one of the things that I have found in my, again, look at me, many years in the software development industry, is that events are a super powerful tool in our toolbox, but I think a very underappreciated one. So one of the things that is a classic indicator about a mature service-oriented architecture, whether you're talking about Stitch Fix or Google or Amazon or Netflix, is the idea that services should at least have the ability to communicate via events. Well, what do I mean? So an event, according to Wikipedia, is a significant change in state. What an event really is, the way I like to think about it, it is a statement that a thing occurred, right? So customer purchased, item sold, customer added, this type of thing. And the idea is that the producer of the event sort of sends that event out into the ether onto a bus, and then maybe nobody's subscribing to the event, maybe one other consumer is subscribing to the event, or maybe many other consumers are subscribing to the event. And typically, those subscriptions are done in an asynchronous way. I fundamentally believe that events are the 4th missing fundamental building block of good applications. So we all know 3-tier applications, right? So there's the presentation tier, there's the application or business logic tier, there's the persistence tier. This is all the stuff that we've been learning and doing for quite a long time. I think we underappreciate that 4th element, which is thinking about events and state changes as first-class objects. And I'm going to show you why, particularly in the microservices world, this is going to give you a lot of power that you otherwise wouldn't have. So, and the other thing I'd like to say is it can feel, when you come from everything in one database and this very simple synchronous interactions through a standard 3-tier architecture, it can seem that events are these really weird things. But you know what? Events exactly represent how the real world works. So events, people who are in the finance industry or are familiar with how finance works, there is no distributed transaction. There is no immediate consistency. When Bank of America and Deutsche Bank are trading currencies, they trade during the day, and maybe they've traded a million different orders back and forth. Those things aren't synchronized immediately between those two parties. They reconcile at the end of the day. In other words, they come back around and they make those things eventually consistent. Another metaphor that I was trying to think of in the last couple of days to make this clearer is your software development process. So immediate consistency would be something like every time you hit return in your IDE, it gets deployed to production. Now, I'm all for continuous delivery, but that seems crazy to me. If anybody does that, I'd love to talk to you afterward. So A software development process is not like that. It is not immediately consistent. So if you say, I can't reason about a system where one part of the system has done a thing and it takes a while for that thing to be propagated over to another end, just think about what you do 8 or 10 or 12 hours a day. When we talk about events and event-driven architecture, sometimes, even if you've been doing it for a while, those words can kind of a bit lose their meaning. The way that I like to think about it, though, is using a workflow. If you can model your process as a workflow, that's events. Okay, so I want to talk about using events in a microservices world, particularly around data. So events are a first-class part of the interface. If anybody was in Dan North's talk just a moment ago, one of the things he said was that events are a first-class part of a services interface, and I thought that was wonderful. In fact, I agree so much I already had it on a slide. A service interface for a service includes every way you can get data or operations in and out of the service. So it includes the obvious stuff, like perhaps the synchronous request response that you have through the front door. So that's maybe REST and JSON, or that's maybe gRPC. It doesn't really matter what the particular protocol is, but that's a first-class part of your interface. But also, the interface to your service also includes events that the service produces. It includes events that the service consumes. And it also, easily forgotten, includes all the bulk reads and writes that you might do to get your data in and out from, say, an analytics system, or a bulk load from some other place. Again, the interface to your service includes any mechanism that you use to get data in or out of the service. Okay. So now I'm going to leverage events to do things that otherwise would seem hard in a microservices world. So coming from a system where we maybe had a monolithic application or a monolithic database, a bunch of things are pretty easy. It seems maybe hard or impossible in microservices. Let's talk about how we might use events to do all those things. So the first thing I want to talk about is joins. So the problem here is that, or the wonderful precondition is that when I have a monolithic database, it's really easy to do joins across different entities in my system, right? Does this make sense? It's just super easy. I issue a SQL statement and done. That becomes a lot harder when all those individual tables in one shared database become hidden pieces of persistence in a bunch of different services. So how are we going to do this? Well, the mainline way that I've approached this is to use events. So one approach here is that you actually have service A that owns table A, and you have service B that owns table B. You do something that in database terms we call materializing the join. So the service A produces an event whenever one of the A things changes, and the service B produces an event whenever one of the B things changes. We have some other service that is listening to the events of changes of A and listening to events of changes of B, and essentially caching those things and materializing the join, denormalizing the join so that it can be queried for the results. Does this make sense what I'm talking about? Yeah, a little bit. Okay. This technique, I'm going to talk about a few more techniques. This technique works best when you have high cardinality A's and B's. When I say cardinality, I mean the number of rows that you would use. So if it's common for you to join together a lot of A's with a lot of B's, this is a technique of essentially reifying or materializing the join or the view in some other service. This technique works really well. If this seems really weird, we actually have a ton of systems that do this all the time, that you probably use without even knowing it. So almost every NoSQL system is some flavor of this idea. Most NoSQL systems don't optimize for the write side, they optimize for the read side. In other words, when you're doing the write, you are trying to set things up in a denormalized way so that the reads are super fast. Again, in database systems, like I mentioned, the way to talk about this technique or this pattern is materializing the view. A view is, essentially a stored query. Materializing the view is actually executing that query and caching it in some place. So other systems that do this are search engines, analytic systems, and log aggregators. So does this kind of make sense? Is this pattern seeming pretty familiar? Yeah, a lot more nods. Excellent. Good. All right. So this is how you can do joins, and this is how events can help you. Oh, sorry. First approach. Second approach is actually joining in the client. In other words, joining in the place where you need the A's and the B's together. So the idea here would be something like, I get a single A from service A, like a customer, and I get the matching Bs from service B, like all the boxes we've shipped to that customer, right? So I get the metadata about the customer on the one side, and I get the metadata or the detailed data about all of the orders or all of the boxes that we've sent them on the other side. And the way to do this is actually having that client service that needs that joined information talk to service A to get the one instance of A, and then talk to an interface of service B that says, give me all the Bs that are represented by this A. Does that make sense? Did the A's and B's super confused? No, I think that seems pretty good. All right, cool. And this works well when the typical use case here is I have a single A, like a customer, and multiple Bs, like all the orders associated with that customer. And so if I want to think about it in sort of entity relationship terms in databases, it's kind of a 1 to n join. Does this make sense? Cool. And the other, I didn't have it on the slide, but common systems that do this are like every web application that you build in JavaScript, right? You go one place to get one piece of data, and you go some other place to get maybe detailed information about that associated with that other piece of data. So you guys do this all the time. Okay. The other thing I want to talk about is how do I deal with transactions in a microservice world? So the problem statement is this. With a monolithic database, it makes transactions, so writing things or updating or inserting things across multiple entities, super easy, right? That's what relational databases are all about. ACID transactions that combine together multiple statements and have them happen atomically, right? They either all happen or they all don't happen. And this is a lot harder when we split our tables up into separate services. There's no argument this is harder, but it's definitely doable, and here's how. So when we split the data across the services, what we absolutely don't want is to have a kind of stop-the-world, pessimistic database transaction across all of those different services. That couples the services together in a way that's pretty awful and slows the entire system down and becomes a real scalability bottleneck. So the way that we deal with this is this. We turn the transaction into something called a saga. Is anybody familiar with the term saga? A few people, more than I expected. Excellent. So the idea here is that we want to model this transaction. In other words, we want to model this case where we want to update some A's and update some B's all together in one unit as a state machine of atomic events. So what do I really mean by that? I said events can be confusing if you use that word. Think about it as a workflow. So I want to update, and here let's imagine I'm updating four things, A's and B's and C's and D's. So I update the A, and that service produces an event that says A has changed. I update then the B's associated with that. That produces one event or several events that says these B's have changed. I do the same for C and the same for D. And we chain these things together as a workflow or as a state machine. And the way to get the atomic aspect, or the way to get the, it's not immediate consistency, but the way to get the system consistent at the end is to do compensating transactions to move back. In other words, I can't just do one rollback and have it all magically go away immediately, but what I can do is have other events that propagate sort of backward through this chain. Does it make sense? So I would say, delete this D, or undo this operation on D, delete the C, delete the B, etc. I was saying things in operational terms. D has been removed, C has been removed, B has been removed. Does it make sense? So you use events going forward to do the forward steps in the workflow, or the forward movement through the forward arcs in the state machine, and then you do the countervailing or the compensating operations in the reverse to undo it. Does this kind of make sense? Yeah, cool. Is this possible without events? Not easy, right? Super easy. It's super straightforward with a system of events. Okay. Just because I think we can't do a conference in 2017 without at least mentioning serverless, which I'm actually super excited about, by the way, this kind of thing is an ideal use of what should generally be called functions as a service, or what has been colloquially termed serverless. So why do I say that? I say that because these little steps in the workflow have super lightweight logic, they are stateless, and they are triggered by an event. So they have the same characteristics that you might be familiar with around like database triggers. An excellent way to model this is some flavor of serverless or some flavor of functions as a service, like Amazon Lambda or Google Functions or Azure Functions. Does this kind of make sense? Yeah. So here's where you can combine serverless with microservices. And just as a sidelight, I don't think microservices are the solution to every problem. I don't think serverless is either. I think that the more tools that we have in our toolbox, the better. And most mature systems don't use a million different techniques, but they definitely use more than one. Okay. So just to bring it a bit to conclusion, in modern software development, we have, we need to do combinations of an organization, which takes the form of small teams, process and practices, which takes the form of test-driven development and continuous delivery, culture, which takes the form of DevOps, and technology, which takes the form of microservices. So it looks like I've actually ended a little bit early, so I'd be very happy to take questions. Köszönöm. All right. Oh, the Slido is great. Thank you for the people who built it and have set it up here. The first question, oh, there you go. You can read it too. What do you think, what is the best practice to maintain the security of a microservice in a DevOps world? Interesting. Let me think about that. I think there are multiple answers to this. I'll give you several of them. Probably not, if you aggregate them up, they probably won't be complete and we can talk more. The best way I have seen services done in a large-scale security done in a large-scale setup, is to have a team of security experts not evaluate security at the end of the development lifecycle, but produce services and tools and libraries that help those individual teams be secure themselves. That's actually the way the Google security team works. So again, when I worked at Google, Google App Engine is a platform as a service. Obviously, since it's exposed to the outside world, there are lots of security implications. There is a security team at Google, and I never met them. Not because they weren't wonderful and weren't doing their job, but exactly because they are wonderful and they were doing their job. They were providing us a bunch of libraries and encoding a bunch of best practices for us to be able to encode into the services. So that, I think, that's the best answer to security, is to have a team inside your company provide the capabilities so that essentially individual teams can do their own self-service. And you will see that this pattern is the same as monitoring, it is the same as operational stuff, it is the same as deployment, right? Have a third party, whether it's your team or some other outside organization, provide the capabilities that you then build on, and it's the individual teams that are responsible for doing the right thing. Doesn't having indirection to divide up the monolithic database create additional latency? Absolutely it does. And doesn't it shift the burden, of scaling to your microservice? Yes, and that's a good thing. So it absolutely increases latency, and that's a thing that you have to design around. So there's no argument that if you have everything in one place, it's faster to do a particular thing. The terrible thing about having everything in one place is it's a lot slower to do everything. Does it make sense? Single bottleneck, single point of failure. That's the problem with a monolithic application and a monolithic database. So it is absolutely true that when we start introducing services and messages, that there starts to be more latency in the system. That's true. But the wonderful property in terms of scaling is in a monolithic world, my only option is to vertically scale the monolith. Right? That is my only option because I can't divide it in half. When I am in the services world, now I can scale all those individual services independently, right? So not only can I put more resources behind the user service and fewer behind the item service or whatever, but also, and this is critical, also I can choose the persistence mechanism that makes most sense, right? If I have a monolithic database, I have by definition made one technology choice. But it might well be that some services are best served by being backed by a search engine or by an in-memory system like Redis or backed by a NoSQL system or a key value store. So from a scalability perspective, actually, microservices make things a lot easier in many ways because it allows you to apply scaling techniques individually to individual services. Services can need shared data. Any strategies? Yes. There are several. One is, there are really kind of two obvious ones, and probably more. So the two obvious ones are this. If a bunch of services need shared data, that's the opportunity for another service, right? And so services can then call in, service A and B can call into service S for shared and get the data from S. Now, they can either get the data from S in a synchronous way when they need it, or they can get the data from S by S producing an event. Does that kind of make sense? In the services world, if there's a piece of data, it's surrounded by a service. Okay. Is not the event system another single point of failure? Ooh, really good. No. I see conceptually why you would say that. But the issue, or the implication, when you build one of those event things, you want to build it in a replicated way. So it's not a situation where there's only one bus that everything in the company talks to, right? So conceptually, there's one bus, just like conceptually there's one internet. But the internet is resilient because it has a bunch of redundant paths, and similarly for events in your system. Cool. What about constraints like foreign keys? Yeah, that's a terrible one. You have to give up on enforcing foreign keys straight up in the database. So typically that's enforced at the application or the service layer. Yeah, so yeah, I get it. I mean, the monolithic world is super easy. I know that is super true. The trick is that when you're scaling, that becomes the bottleneck for, for feature velocity and performance and so on. So yeah, great question. And yeah, everything's a trade-off, right? Once you cross a certain scale, though, microservices seems to be the general approach. And I don't say that just because I have done that. I say that because every big company that you can think of has typically started with a monolith and ended up with something that we now call microservices. So that's true of eBay, that's true of Amazon, that's true of Netflix, that's true of Twitter, that's true of all the large companies that you can think of started with a monolith. That became a scaling bottleneck, and they broke it up into individual things that we now call microservices. Okay, wow. So in joins number 2, I'll see if I can find this. No, you can't do that. All right. So in joins number 2, service B's isolated persistence has a foreign key in service A's ID. That is right. So this is a situation where, if you remember back, this was the one A with many B's, so one customer with many orders. Isn't it no longer isolated then? No, because the reference back, in the same way as you design the database table, the reference from B back to A is just an ID. I hope that's helpful. So essentially the foreign key that would live in the B side, so the fact that the orders are associated with customers, in that service it just remembers the ID of the customer that it's associated with, just exactly like a table. So I guess I'll take one step back and say two things. I'll say, when you enter the services world, lots of times people feel like they don't have an intuition around how services should be built, and I think you know a lot more than you think you do. This is certainly true of the teams that I work with. So people say, I don't know how to draw the service interface boundaries. I don't know what should be in there. And I say, do you know how to design a class? Like, oh yeah, I encapsulate the data inside there and I have a simple interface. You know how to build a service. And from the data side, you can do something similar, where I don't know how to put data, which service to put data in. Do you know how to design entity relationships and have tables talk to other tables? You just designed how services work. So yeah, you know more than you think you do. Whenever an entity changes, do you always pass its whole state between services? Excellent. Or only what's relevant for the event? Very nice, very subtle, and nuanced question. The answer is it depends. It's a very interesting question, and therefore the answer is it depends. But I'll give you some more nuance there. So often, if you are worried about the ordering of events, the typical way to do it is you think of an event as a notification. You say something like, customer changed, or maybe something more detailed like customer address changed. And then often, if you're worried about order of operations, the receiver of that thing will read back to the service that sent it and said, give me the current state of that customer, or current state of the address. Why would we do this extra dance? It's because if you're worried about ordering, those messages can come out of order. So I might get something that says, the customer address changed, And if I encoded that change in there and stored it, there might be a bunch of other changes queued up, or that customer might have been deleted somewhere in there. And I lost the other part of it, which was how do you deal with deletes? That is a little bit more subtle. That's going to be hard for me to do in words quickly. But the correct way to deal with it when you have to be sensitive to event ordering is you have to remember deleted things. If you take away one word from that question, it's called tombstone. So go read up about what a tombstone is, which is a representation of a thing that is deleted. And because events can arrive out of order, it is actually possible for me to receive an event that says order deleted before I receive the event that says order created. And the critical thing is for me to remember that I saw that deleted event for a while so that I delete the customer in case it shows up. Does it make sense what I'm saying? Okay, more nods than I was expecting. Thank you, awesome. Okay, keeping microservices backward compatible and versioning them could be hard, totally hard. Well, actually not so hard. Any advice for doing it right? Yes. In the same way as you work hard to keep your class interfaces backward compatible, and you know very explicitly when you change what kinds of changes will change that interface, i.e., do you have to go around and update the rest of the code or not? You already have a sense for what's backward compatible and forward compatible. One of the slides that I had expected to be in here but seemed to have gone off into the ether was the discipline around forcing those microservice interfaces to be both backward and forward compatible. And that's the way that you can get the ability to update and change those microservices independent of each other, right? If every change that I make, every time I change, every time I change the interface, I would want to prefer changing the interface in a backward compatible way, right? So that means I don't change the signatures of any of the methods that I currently have. So maybe if I'm adding new capabilities, I add new methods. In the case that I do, and those are, if you use semantic versioning, those are minor versions, right? So not the first number, but the second number. So yeah. And then I lost it. Versioning, yeah, breaking changes. So if you have a breaking change, that does require all the other services to update themselves. And the tip, and that is in semantic versioning, that's updating the major version. That does require changes on the part of other services. So the typical way I have seen that done properly is you actually, if you still have, well, because you still have clients that are using version A of the interface and you want to upgrade them to version B, you actually have to run them both in parallel for a while. Does it make sense? You have to keep the A going for the clients that are dependent, or the other services that are dependent on A. You spin up B, and then you encourage the clients to migrate from A to B. One of the benefits of the DevOps approach that we adopted Stitch Fix, that we did at Google, that we do at Amazon, is if you own end-to-end your service and you also operate it, it means, or sorry, if I as a service team am owning my interface, own my service end-to-end and own the operation of it, it is strongly in my interest to help you migrate from version A to B. Do you see why that's true? Because I desperately want to move to B, and I don't want to have to maintain and operate both those systems. So it is strongly in my interest to say, hey, other team, this is deprecated. I'm going to continue to support it for 3 months or whatever you can negotiate with that team. At the end of which, between now and then, I want to make sure that I help you migrate. And again, it's strongly in my interest. It helps me and my team do less work to help you migrate. Does that kind of make sense? Good. Any advice for doing it right? That is my advice. Mostly be backward compatible, except where you can't be. When you can't be, run two incompatible versions in parallel, and migrate clients from the old to the new, and then shut down the old. About sagas, you had a simple linear workflow, but surely the workflow is sometimes a graph. Absolutely true. Thank you. Absolutely true. How do you handle the compensating steps for less trivial sagas, in other words, more complicated sagas? Yeah, well, so for each step forward in the graph, there's a step backward. I'm sure you can construct a graph for which there are diamond shapes, and we can talk about that over beer. But yeah, the conceptual idea is you move things forward when you're kind of producing the saga, and then you move things backward, undo them with compensating transactions, or rather, sorry, compensating events when you're undoing the saga. Can you mention an example where microservices are not the solution? Oh, many. When you are starting out. So I didn't give this talk here, but I give this talk lots of places about pragmatic microservices and migrating from monoliths to microservices. Monoliths are a wonderful thing. Remember all those things that are easy, that used to be easy and are now hard? Well, guess what? If you don't have the scaling problems of a Google or an eBay or an Amazon, you are early in your life cycle, you're still trying to figure things out, you totally should build a monolith. Why? Because any extra effort you spend on building the wonderful distributed microservices system is time that you're not spending figuring out whether you have a business model, figuring out whether you have product market fit, and delighting your early customers. So of many examples of where monoliths are entirely appropriate, that's one of them. When you are early in your life cycle and you don't have these kind of scaling and feature velocity issues. So it is flashing that my time is up, so I hope you enjoy the rest of the conference. I'm going to be around the whole time, so if you have questions or comments or criticisms, I'd love to hear them. Thank you. Köszönöm.